the weird shit I say. Let's see. Okay. So, from section 12.2, we got up one level in the Van Hilly level of understanding of geometrical concepts for students. Let's see, do I have something that's a little less? No. We got into symmetry, line symmetry. We also got into rotational symmetry. So if I have an isosceles triangle, there's obviously one line symmetry. In terms of rotational symmetry, can I rotate it part of the way and it would match up with what it started off as? Or do I have to rotate it all the way around?
All the way around.
Yeah, if it's truly isosceles and not equilateral, this is truly isosceles, not equilateral, I have to rotate it all the way around for it to match up with itself. Is everybody with me? Okay. What if I have an equilateral triangle? What's the rotational? So this has no rotational symmetry. We don't count a full rotation. That's a little bit like cheating. Like, nope, didn't work for you. If I have an equilateral triangle, oh my God. Everybody pretend like that's an equilateral triangle. It had a rough weekend. Poor little dude. How many line symmetries are there? 3. Because and how many rotational symmetries? So if I rotate it, if I really make, come on, John. Okay, there we go. If I rotate it once, oh God, pretend like that's good. I should, if it's truly equilateral, how many rotations besides a full rotation will it line back up on itself? 2. I love it. If I rotate it once, this will become here, right? And then rotate it again, this will become here, and then the third time is the one we don't count, because that's the full rotation. And anything is good with a full rotation, yes? All of us are perfectly symmetric if you rotate us 360 degrees. So it doesn't really count. So it's got kind of like 2 rotations. We got into identifying different types of quadrilaterals. And that was from 12.1, but then we started talking about symmetry and rotational symmetry for quadrilaterals, so the same idea. If I have a square, square is neat. How many line symmetries are there? Yeah, you might say 4, understandably. Why is there more than 4? So when you say 4, and don't worry, whoever said 4, you're fine. Where were you thinking about? Were you thinking about like in the midway of the top line segment? Yeah. Okay. Now of course there's twice as many as that, because where else works? Through the diagonal. Not twice as many, you gotta be careful with. So I got 1, 2. Oh, I think when you said 4, you might have been fine. 3, 4. Yes, okay. So 4 is fine. I was counting too much. What about rotational symmetry? 3. I like it. Because again, we don't count the full rotation. That wouldn't be right. So if we turn it by 90 degrees, it lines up. Another 90, it lines up. Another 90, it lines up. Is that cool? Okay, all right, not too bad. Now, of course, we can get some slightly funkier shapes, but you stop and consider the same way we do here. Okay. There's a, well, maybe I'll bring that out at some point. Yeah, okay. One last thing I want to ask you about. If I wanted to show that these two lines are perpendicular, line L and line M, and I don't have a protractor, I don't have anything, I just have the piece of paper that I drew it on, how could I do that? What do you guys think? Yes? No, I could draw it, but it doesn't mean that it's true. You know what I mean? I don't have anything except the piece of paper I drew it on. Yes? So let me ask you this. If I have, are these perpendicular the way I've drawn them? Are those perpendicular? All right, what does perpendicular mean? They meet at what angle? 90 degrees exactly. Now I've made it really obvious in the last one I just drew, is that perpendicular? Hell, that's definitely not a 90 degree, yes? This angle here is bigger than that angle there, yes? And what are these two angles, this angle and that angle, what do they add up to be?
180.
Yes, because it makes a line. So if one of them's bigger than the other one, neither one can be 90 degrees. Now, what if I fold that so that line L folds on itself? What would I see that would tell me that M is not perpendicular?
One side would be longer than the other. One side would be longer than the other.
Not longer, necessarily.
It'd be a little off.
Be a little off, yeah, exactly. So if I want to prove that L and M are perpendicular, I could fold the paper along L, and then what should M do if it really is perpendicular? It should fold right onto itself, right? If I look through the paper at a light, I should see M covering itself. Okay, I love it, I love it. So there are some investigations we could do just involving folding. Later this semester, we're going to start messing with protractors and rulers and so forth and constructing things. But if I have something in front of me, I want to check to see, is this truly perpendicular? And I don't have a protractor, I can just fold the damn paper and see. Okay, now of course, you know, we're not going to be 100% correct all the time. It could be off by 0.001 degree, but in terms of human, we're good. It's good enough for government work. Okay, so I think I want to go ahead and do this. Yeah, I like it. Yeah. Yeah, I didn't mean to do that one. It's okay, Jeff. And then that didn't work. We'll see how that, yeah, that's unfortunate. All right, so I desperately tried to, well, I'll show you. Let me pass all these out. We'll get into groups. This is kind of practicing stuff from 12-2. Let's take a look here. Somebody noticed something really good. What were the instructions for this page?
Draw a line of symmetry on each shape.
Yeah. A line. But I really appreciate, might as well find all of them, right? But this could be like the very first worksheet for students. So if they find one, then you can start to say, did anybody find a different one? And then you can kind of build off of that. Now some of these only have one, yes? Like, what about this guy?
One.
Yeah. So he's only got this one here. Did anybody find another one? If you did, I want to talk to you. What about this dude? Anything works that does what? How can you describe what works? As long as I go through, I don't know how you want to describe this, a tip and an ingress, a kink, I don't know. So as long as you go through an edge of the star here, and a little valley, a hill and a valley, does that make sense? You guys with me? Did anyone draw that one? Now obviously so that's 1, correct? And then there's 2, 3, did I miss one? 2, 3, 4. And then they start to repeat, yes? So there's this one, it's 1, 2. There's this one, 3. And there's this one, 4. And there's this one, there you go, 5. And then they start to repeat. So it kind of makes sense, it's a 5-pointed star. It kind of makes sense there's 5 lines of symmetry. Be careful, don't count them twice. They start to overlap, so then it's already been counted. What about this guy? 1. Yeah, there's 1 here. And really can't be any other ones. Now a quick word about rotational symmetry. These two, do they have any rotational symmetry? Nope. This one, yes. If you follow this around, 1, 2, 3, 4, and then it's back 1. Okay, I love it. What about little heart dude? 1. C dude? 1. What if I put the letter O? Why would that be a little evil? Just pretend like I drew that perfectly.
It has unlimited lines.
Yeah, what do you guys think? How many officially lines of symmetry are there through this? Infinite. Kick ass. Kick ass. How much rotational symmetry is there here? Infinite. Yes. Every little tiny rotation I could do. And then about the tree. 1. And what about this here? What is this? Hexagon. How many?
6.
Yeah. So if we go 1, 2, 3. You gotta be careful. 1, 2, 3, 4, 5, 6. Yes. And of course, don't double count them. What about the letter D? 1. What about the egg dude? 1. And of course, the H dude. 2. You got 1 right down the middle there, 1 right down the middle there. Of course, rotational symmetry for H. How many rotations would make it line back up? 1. And then a full one we don't really count because everybody's got that. Okay. You'll see some books that count the full rotation. But you know, I would say that a shape that's got no symmetry has no rotational symmetry, but everything, if you rotate it once, lines back up with itself. Okay. Now, these are a little tricky to do by, so here's the thing. Some of your students are going to have better spatial reasoning than others. It is something that we're just kind of born with a certain amount of it, and we can develop more of it as we go through our lives. Some people have very little spatial reasoning, and some have like a silly amount of spatial reasoning. So you kind of need that to think about what's going to happen. Now, you could have just folded the paper. But if you look at it, how can you tell number 3 what the answer is? And why is it really good to call that line M? One group knows.
Mirror.
Because it acts like a mirror. And if you teach this and you don't say the word mirror as you teach the idea of symmetry, you don't make any sense. Because a student can think, if I put a mirror there, can you tell me exactly what you would say to have a student know 3 is no in words, not by folding? What could you say to the student? Or even what can you say to me? They're not looking at each other. That's beautiful. When I look at my reflection, he's looking at me, yes? So the tip of the arrow should be as far away from the mirror on the other side as it is on the original side. So that blue, this blue tip should have a red reflection as close to the mirror as it is. And that's one of the immediate things you look for. So if you think about that, what about number 4?
No.
Why not?
Because the red is a little bit closer than the blue.
Yeah, if you think about it, this side should have a side right across from it, yes? Do you see how that doesn't work? Do you see how you can start to break it down if you take, now let me see, what else could I say here? That's the first thing I saw was there's that curved side, and the curved side is not in the right place, yes? You can see it. It might be easier even if you just tilt the paper, and then you can really see it, yes? That is very much not the way it should be. Okay, maybe. What about number 5?
Yes.
Yeah, that one's good. So you can see a straight line from there to there, there to there, there to there, there to there. Yes? Okay, I like it. Okay, and of course, I don't want to get into that, but it's not necessarily perfect. But we're just trying to get the idea. Like, if somebody said, well, the blue one's a little bit bigger than the red one, that's maybe not, I don't know. No. The main idea is just how far is every important aspect from the mirror. Is it equidistant on both sides? Okay, I like it. So that's a way to look at symmetry without doing any folding. This is another kind of idea of symmetry without folding, and it's the same idea about distance from the mirror. And I do apologize for one group about mishearing what they were saying about this one. So of course, line segment AB reflects to what?
Yeah.
That's crazy sauce. What reflects to DEF? By the way, what is this symbol? Angle DEF, yeah. Yeah, so DEF goes to what again? DAB. I like it. I'm not going to make any stupid dancing jokes. C, point C, of course, reflects to G. Here's the one. D reflects to D. What reflects to angle GFE? So let me see. G. Oh, this is neat. GFE. CBA. Exactly. You can even go point by point. G goes to C, F goes to B, E goes to A. And of course, what goes to line segment DG? DC. Kick ass. Yes?
So when we put the answer, we have to put the lines and angles?
Totally.
Okay.
Because otherwise, you're not identifying what the shape is. If you just put EF without a line segment over it, it actually doesn't make any sense. Because like, if I just say DEF, you could actually talk about triangle DEF instead of angle DEF, yeah? So then I would put a little triangle in front of DEF if it meant the whole triangle that would make. Yeah.
Just in general, does it matter what order the letters are in? Like, let's say if I put EF instead of FE, does that matter?
I was gonna say, okay, perfect. What do you guys think?
Yes.
It's a little important because, like I said just a minute ago, to identify some of these, you can go point by point. So A goes to E, B goes to F, so AB goes to EF. I'm sorry, yeah, E. Technically, it doesn't matter because they're both referencing the same line segment. Now, when we get to stuff like rays, does anyone remember what a ray is? Besides the second thing in the do re mi.
So it doesn't stop on the other end?
Yes, it doesn't stop on the other end. So if you say ray EF, that's very different from ray FE. Then it really is important. But with line segments, I totally agree with you. You can identify the line segment, it's just kind of its name. You can call it the other way around. Okay, like my name is Waller, Jeff. You can call me the other way around. Where'd you go? Yeah, okay. 12, if well, I could have maybe done this. I do have some scissors, but not quite enough. Well, can you guys imagine? I don't know if anybody read through this. If you did do this, how would they relate?
They mirror each other.
They could mirror each other, yes. They're obviously congruent because of the same triangles. But what's really neat is if one mirrors one and one is if one is exactly the same image and one's a reflection, or does one, so anyway, that's a good exploration to make. I just gotta get a few more scissors. This one was the one that's a little hard, so I redrew it. I just drew it on this, so let me see if I can get this to work. So I put this like this. I think this should work, roughly. And then, let me think, is this one? Yes. If you fold this along, so M, so I got M right on the edge here. And then if you look through, if I move it a little bit, I can see, let me see, I need to make you do this. There. Almost. If I move it just a bit, I can see the line underneath. So according to my pathetic human skills, I would say that's pretty good. It looks like I went off to the side a little bit at the end of the poor little line. So if you said yes, then you're good. I would agree. So I folded it along M. So I made M right on the edge. And then I looked through. If you just crinkle the paper a bit, you can see how it does line up with itself. Is that cool? And like I said, it's a little bit easier if you do it on another blank sheet of paper. So I gave all of you guys a blank sheet of paper at the end because it didn't line up. So again, here it is. This poor thing. Here's this. Fold it along M. And then see if L lines up with itself. And ignoring the end of that, see that? See the end of that? I think it looks pretty good. You know, this is me drawing, so I think that was just me going off to the edge. So according to my pathetic little tracing, I'd say it looks good. You see how it lines up really well with the first part of the line? Spam. If I try to do it with this, let's see, I don't think it's going to work well because it's got a lot of crap on the other side. So if I fold it along M, see, I got stuff on the way. Oh, it does look like it's off. Let's see. Might just been my bad tracing. It does look like it's off. Does it look like it's off a little bit? All right, so it was my bad tracing. Okay, so you can make it out there. It does look off a bit. Okay, my fault. When I traced it, I probably went a little squibbly. Okay. What about this guy? I had a few people not quite understand what it was asking. Focus all of your attention on line L and fold it around point P so that line L lines it back up with itself. So if I kind of fold it a bit, I can see it doesn't quite line up, and now it's lined up. Now look at M. So I made L perfect, yes?
Yeah.
You guys see if I squunch it over that way, and then I can squunch it this way, perfect. Perfect. How about M? Is M just as good? No. So it is impossible that it's your folding that's the problem. Also, it's impossible it's my tracing that's the problem because I didn't trace this one. So this is verification that they are not parallel. How far from parallel are they? Not very far, which is why on site, if I gave this to you on a test and I said, are these parallel? I would understand if you said yes. But they're off by just a little bit. So when are they going to connect with each other? Way down there because it's barely off. So any two lines that aren't parallel, if you follow them long enough, they will eventually meet, yes? So these will probably take a long ass time to meet because they're just barely off. I love it. Okay. Maybe. So there's a lot more you can do with just folding to investigate a little bit higher level geometric ideas. The idea of perpendicular and parallel are higher level ideas. They have a lot going on. They have an understanding of right angles, they have an understanding of angle, they have an understanding of orientation. There's a lot going on with it. But to investigate it, you just fold a piece of paper. That's crazy. Okay. Yeah, okay. I think that was it. This poor little thing has been mushed. Alright, guys. I was on Team Chameleon there, apparently, so. Go team. Alright, so. I forgot that this book doesn't have a ton of videos. I don't think I showed any videos from chapter 12 yet. So I'm going to show you chapter 12. So with this Ben Healy theory, level 0, does anyone remember what level 0 was for students? If you're at a level 0, so it's recognition. Can somebody tell me what kind of mistakes a student who is only a level 0, what kind of mistake they can make?
If something doesn't look like their idea of a shape, they won't recognize it as that same shape.
So what could I do to a shape?
You can twist it.
Yeah, if I rotate a square, they might not identify it as a square. They might say it's a diamond or something, and not realizing it's still a square. Or any shape, right? So rotations kind of throw them off. Reflections can throw them off. So they have a very idealized image of what something can be. Do they have trouble realizing that squares are specific kinds of rectangles? Yes. They're not breaking the image into its defining parts. They just have this holistic idea of a triangle. And we saw that when I showed you the videos that I almost showed you again today, where they couldn't quite see it was a triangle if it didn't match with their idealized version. Right? Have any of you guys heard about, well, this is a weird thing to talk about, Platonic solids, where, anybody heard the cave and anybody ever done philosophy?
Yeah.
The, what's it called? Ideal, no.
I went into this like a year ago.
I can't remember the name, but there's this idea that there exists a perfect triangle somewhere, and all of the triangles are kind of like just shadows of that perfect triangle, and that's what we're watching. Okay. We're gonna look that back up. It just only came to my mind.
Like
Aristotle, one of those guys. I thought it was Plato, maybe. Anyway, so when you're at level 0, you have a very specific idea in mind of what a triangle is, and you have trouble with something that doesn't match that. When we move up to level 1, what level am I at now? Analysis, cool.
It's the allegory of the cave.
There it is, thank you. Where he's got like a light shining, and you're watching the shadows on the back of the cave, and that's basically like what we're doing in life. Anyway, too early on a Monday for philosophy. Okay. Focus. Level 1, we call the analysis level. And this is where they start looking at the actual characteristics. They start to realize what it takes to define an object. Therefore, rotation won't throw them off, because they've identified that a square has right angles and 4 equal sides. So it doesn't matter if it's rotated, as long as it has those parts, it is a square. You guys kind of with me? Okay. And so you have your definitions of the various quadrilaterals. They start to kind of like take those definitions in, and then they can apply them to a worksheet and identify things correctly. So level 0, they're not going to circle all the triangles. They're going to miss some. Level 1, they're going to get their triangles for the most part. I think I can't remember now. I can't remember how far we made it here. We talked about Well, we did. We talked a little bit about the square dot. The square dot in your kit. The pegboard. Square pegboard. There's also square dot paper that I might bring in at some point. Same idea, but then you can draw stuff on the paper instead of putting rubber bands, so you don't have to arm your students. This kind of brings us to the idea of a line segment. Because if I have squared up paper, I can obviously connect two of them, make a segment, a line segment. And we already know that we identify that as AB like this. I can have an angle. If I connect some dots, I can make an angle. Now very quickly, I cannot remember where we left off here. How would I identify that angle? What would the name of this angle be?
ABC.
Yeah, I can say ABC. Could it be any other name?
CBA.
Could it be any other name? Yes, one more name. That would work also. In this case, angle B does describe that angle. I like it. So, how could I kind of mess it up? What if I had this situation here? Now, does angle B actually have a meaning in this?
No.
No. So how would I identify this angle here?
Angle CBD.
CBD, that's right. Okay, nothing major. This is all good. What does anyone remember? Does anyone know what we call the point B? Do you guys remember with parabolas? What would you call this point right there?
Oh, starts the V.
Starts with a V.
Vortex.
Vortex.
I like vortex, but no,
Vertex.
it's vertex. Yes.
Thank you.
You're welcome. So it's kind of like if I straighten the sides of a parabola out, we still call that the vertex. Cool. So angle, so not angle, but point B is the vertex of how many angles in this picture?
2.
So we got angle CBD. What's this angle?
ABC.
ABC, and what's the other angle that I haven't talked about yet?
ABD.
Good. Notice how in every name, now of course I could also call this CBA, but in every name, where's the vertex point?
In the middle.
Right in the middle. Cool. So that's how I quickly identify. I can't use angle B. Let me make this really, really clear. This, not good. It's not descriptive enough. There's too many things that could be. Why was this okay? Because there's only one thing that could be. Okay. I don't think this book does this. This is better in a way because then there's absolutely zero ambiguity, and also just makes it more generally the same, no matter what the situation is here. Okay. Blah, 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 blah. Yeah, I think, let's see. Yeah. I think we talked about the different kinds of triangles, yes. Isosceles, equilateral, right. There's isosceles, equilateral, right. Now what's really interesting is, what's a scalene triangle? Let's see if they have, there we go. No. What's true about isosceles triangles? What is the most important defining quality of an isosceles triangle? Two sides that are the same length. So if it has exactly two sides that are the same length, it's officially just isosceles. What makes something equilateral, of course?
All sides are
All sides are equal, right? Now, a right triangle, could it be equilateral?
No.
Hell no. Can you tell me how you could explain that?
Right triangle has a 90-degree angle, which means none of the other angles.
In an equilateral triangle, how big does each angle have to be?
45, right?
How many total degrees in a triangle?
180.
180. So if I have 3 angles in a triangle and I have an equilateral one, every mouth opens the same amount. So how big is each angle? 60. So right triangles are out. They can't be equilateral. Can they be isosceles? Hell yeah. If this is 90, all I need is this and this angle to be the same, which would make them both. What would these be exactly? What number? This is 90. What would these be? 45. I like it. All right, let me stop for a minute. Love you guys. Does a right, so isosceles must have 2 sides that are the same length. Equilateral must have all 3 sides the same length. Scalene, something about the side lengths. If I'm not isosceles and I'm not equilateral, that must mean I have how many sides the same length?
0.
None. Good. So all sides different lengths. And so a lot of right triangles are also scalene. Scalene's a little weird. You guys have heard that word before, but I don't know if you have a really good definition attached to your when you think about scaling. But that's all it means. Just all the sides are different lengths. So a lot of right triangles are also scalene. Okay. We already kind of talked about the folding test for parallel and perpendicular. That was on the paper. I think, yeah, good. And I already did this. It's beautiful. Yeah. So let me show you this. This is a beautiful example of what a student should have in their head if they have mastered level 1 for quadrilaterals. This is on page 575, by the way. So level 1 is all about breaking down the important parts of the shape that tell me which thing it is. So that, therefore, rotation won't mess me up, reflection won't mess me up. I like it. So if you go through all these, which one has the most X's? Square, because it's the most little perfect dude. Rectangles are squares that have been messed up a little bit in one direction, if you want to look at it that way, yeah? Rhombuses are squares that have been messed up in a different way. And then parallelograms have been messed up in both ways. I don't really like saying messed up, but you know what I mean. Start with a little square, and then you lengthen it. Rectangle. Start with a square, and then you push one side and push in the other side like that. Rhombus, right? And then you stretch it again, freaking parallelogram. And that's why you keep losing things that it meets, requirements that it meets, because you keep smooshing it and moving it, right? So the minute I make it skewed, it's lost its right angles. So I love it. Okay. This is the kind of thing that a student who has mastered level 1 for quadrilaterals would be able to tell you. What are the attributes? Yes? Level 0, if I say, tell me the attributes of the square, they might draw a square, they might say it's got 4 sides, but they can't necessarily articulate the definitions of what's going on. Okay. Okay. Ooh, good. All right, so I want to get a little bit into 12.3, and then we'll call it a day. what 12.3 does, it doesn't really continue, well, it does, sorry, I'm getting a little ahead of myself. Now we're level 2, relationships. This is where you really start to solidify that a rhombus is a parallelogram is a rhombus is a special parallelogram. A rectangle is a special parallelogram. Yes? And you start to make this hierarchy of things. So let me see if you guys can get this. If I wanted to make, let me get a little ahead of myself. Sure. If I wanted to make a hierarchy of the most general kind of four-sided shapes, that would be quadrilaterals. So there's a whole lot of quadrilaterals. They don't have to have anything about them. All they need is 4 sides. So sort of like you can make a scalene triangle that has no sides that are the same length. You can do the same thing with a quadrilateral really easy. So can you draw right now a quadrilateral, every side is a different length, and no sides are parallel? Can you draw that? Every side is a different length, and no sides are parallel. This is the kind of thing I'm really curious how people do this. So I want a quadrilateral, every side is a different length, and no sides are parallel. So the way I'm thinking about doing it is I would start with 2 lines that are not parallel, and then I would connect them. So every side's a different length, and no sides are parallel. Yes? Is that cool? Now, I'm curious, did anybody just kind of like go for it and then hope you don't accidentally make something parallel or something? Yes? Okay, I like it. So you've got this idea of quadrilateral. It's any 4-sided shape. Do any of the angles have to be anything specific? No. What do all the angles have to add up to be though? 360. I like it. Because if I drew a line connecting any diagonals, I make 2 triangles. That's one way to look at this. Okay. Later this semester, in fact, really soon, to be honest, we're going to start to formalize a lot of what we're talking about. We're going to start to prove some of the things that we kind of take for granted. Like, for example, the fact that triangles have 180 degrees total. We're going to be able to prove that. And some of you guys are like, I'm fine if I can't. Well, no, you're going to be able to. So if I want to drill down and make this more specific, so I've got quadrilaterals. Let's start over again. What is the first kind of level of, let me see, how can I say this? I want to go to the next kind of most general shape, and there's a few different directions I can go in. Did anybody, if I make a 4-sided figure where none of the sides are the same length, what could I draw accidentally? And could I make 2 of the sides parallel, but all 4 sides are a different length? Mm-hmm. You with me? What shape would that be?
Trapezoid.
Trapezoid. So if I take this and I just make this parallel and then connect these, that now is specifically a trapezoid. Yes? And a trapezoid is exactly 2 sides are parallel. So that means the other 2 sides cannot be. So a trapezoid is sort of like on the side there. Is a parallelogram a type of trapezoid?
Yes.
Considering the definition of trapezoid is exactly 2 sides are parallel.
No.
No. So it would be a different kind of like branch. Yes? Over here I've got parallelograms. And remember how to spell the word parallel? It's got parallel lines in it. All right, let me stop for a minute. Your students are going to start to kind of piece this together as they learn the definitions. Something like this is a really good way to organize their thoughts. I want this to make sense. A quadrilateral is any four-sided shape. Now, how can I start to make some conditions? I can make two sides parallel. Okay, that's trapezoid. What's parallelogram?
Two sets of parallel sides.
Two sets of parallel sides. And now both have to be parallel. And then how can I make that more restrictive?
They have the same length.
Yes, and what would that be if I make them the same length? No, if I take a parallelogram, but I make all the sides the same length. Imagine a general parallelogram.
Oh, equilateral.
Careful now, that would be a triangle. Right?
A rectangle.
No. Can everybody imagine just a general parallelogram? You guys got it? Are there any 90-degree angles in that general parallelogram? No. If I just make every side the same length, what have I got now? A rhombus. Now, if instead of making every side the same length, what if I made every angle the same? If I make all the angles equal. If I make all the angles equal, they all have to be 90, because they have to add a 360, right? So if I take a general parallelogram and I make all the lengths the same, rhombus. If I take a general parallelogram and I make all the angles the same, I get
Square.
no, not quite. Rectangle. All I've done. So same length rhombus. All angles equal rectangle. So let me do this. Start with a general parallelogram. I can do two separate things. First off, I can let go of the fact that this is required. It's good. I could smoosh it this way so all the sides are the same length. That's rhombus. Or I could grab the sides and go like that. That's a rectangle. If I do both of those things, then I finally get myself
A square.
a square. So a square is a specific kind of rectangle. A square is a rectangle where all the sides are the same length. Can you make a similar statement relating squares and rhombuses?
A square is a rhombus with 4 90-degree angles.
Beautiful! So to make a rectangle a square, I just have to condense it in some direction. To make a rhombus a square, I have to straighten out the angles. Yes? Okay, I like it. And these are all things we know. You guys just never really maybe made a little hierarchy like this. Okay, I like it. This is what's happening at level 2 for students, is they stop seeing every shape as its own distinct thing, and they start becoming variations on something else. And in order to be able to make that step, you have to understand the definitions of each shape and how they fit into each other. Alright. Alright, let me see. I got a little ahead of myself. It's gonna be okay. Blah, 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 blah. Yeah, so a really good question we already answered earlier as to ask a student. If they understand triangles, check. And they understand right triangles, check. And they understand isosceles triangles, check. Boy, that's a horrible isosceles triangle. I'm gonna be okay. Then you can ask him a question like, can an isosceles triangle be a right triangle? And we already talked about that earlier. Yes? This is kind of the first thing you can do to get them from level 1 to level 2 is to start asking them, all right, if you say it's a rectangle, does that mean it can't be a square? You know, then they start to realize that the lines between things are not strict. Things can go across lines between things. Okay. Blah, 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 blah. Ooh, no. Oh, that's funny. Sorry. I just had a picture on here that I drew. Is that, well, let me just say this. That's isosceles. So I can see these angles are the same, these sides are the same. So I'm going to start to introduce these symbols that I'm sure some of you guys have remember seeing, but everybody's seen them. Do you guys remember these symbols?
Mm-hmm.
This means that these two sides are
The same.
the same lengths, are otherwise called congruent. Now, are these two sides the same side? That's kind of a silly question, yeah? No, Jeff, they're on different sides. They're different sides. So the word congruent means they're different things, but they have the same length. And the same thing with these symbols, right? For this angle, I would put this symbol because it very obviously is not the same as the other two angles. Real quick, from my picture, understanding I draw horribly, but I've made it really clear here. Is this angle less than or bigger than 90 degrees? Bigger than 90 degrees. Can you imagine, in fact, you could do this with like a compass or something. I've got a really big compass, and you can just sort of like push it in. So if you can imagine pushing that in, can't you make it so that now this angle here, same triangle, I just push the sides in. This angle here is now how related to 90 degrees?
Smaller.
Smaller than 90 degrees. So somewhere in between the two, there must be a place where it's exactly 90 degrees. And it's still the same isosceles triangle. It still has the same side lengths here. Okay. So therefore, there is an isosceles triangle that is also a 90-degree triangle. I like it. Oh, yeah, I don't want to do that. That's right. Yeah, we already did all this. It's beautiful. Blah, 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 blah. So real quick. Can everybody attempt to define what a square is? All right, who's got their definition? Who wants to share it with me? Yes.
A quadrilateral with 4 equal sides and 4 90-degree angles.
Quadrilateral with 4
Equal sides and 4 90-degree angles.
Yes. Anybody define it differently? Yes? Good.
Is it a parallelogram with the same angle and same length?
Okay, cool. I like it. So it's a parallelogram. So instead of saying quadrilateral, which is beautiful, this is beautiful, cheers. You could say it's a parallelogram with equal sides and equal angles. Yes? Okay. Anybody else got a different way to define it? We can start with rhombus. You say it's a rhombus. You could say, this is what's cool, you could say it's a rhombus with the same angles, or it's a rhombus, well, that would be what it would be. So you can say it's a rhombus with the same angles, or you can say it's a rectangle with same sides. All the sides are the same. Yes? Okay, cool. This seems kind of silly. The one I was given was beautiful. That is the most broad way to define it. But then you can start to define a square based on adjustments you make to another shape, just like we did earlier. And every time you redefine a square, starting at a different place, you're solidifying for a student the connection between all these shapes. A couple weird little side notes. Does anyone know what? So here's some other quadrilaterals. I'm going to call them the exotic category. Kite. Now, if I said, draw a kite, could you guys draw a kite? Is anyone willing to come up and draw a kite up there for me? You're just ready, come on. Just right next to where it says kite, draw a kite. I like it. Thank you. Perfect. A little tail. Yeah. Okay. By the way, real quick, have any of you guys, where's that, what's it called, Mission Bay? It's a really good place to go kite flying. And you see these nifty ass kites. And one time I saw this little, this is terrible, it's really windy. And this dad was out there and he gave the kite to his little person. And the little person just started getting dragged along. And he ran after him like, that's not, no. You lose kids that stuff. So, would you all agree that this is what you would draw? Can anyone identify the thing that made this a kite? What defining quality makes this a kite? What's really cool is, all right, let me see. You guys can do it. Look at the sides. Is there anything that has to be true about the angles? If she would have drawn the top a little bit more out, would you guys have freaked out? Like, couldn't a kite look like this? Doesn't it have a bigger angle than that? So does there seem to be a defining quality of angles required for kites? You guys see what I'm saying? A kite, you don't talk about kite. When I say kite, you all have an image of a kite, but a kite is a specific name for a shape. And it's more than you think. Can anyone see the defining qualities? Look at this, since it's not angles. The angles can be whatever the shit they want to be. Because couldn't I make the chin of this thing long? Yes? And it would still be a kite, yes? Or I can make it short, still be a kite. So the angles don't matter. What is it that matters?
The sides.
What about the sides?
They're two sets of equal sides.
Good. So these two sides are congruent, and these two sides are congruent. So it's two sets of equal sides. We say like it's two pairs of equal side lengths. So let me ask you a very strange little question here. And notice how they're kind of across from each other like this. So is a parallelogram a type of kite? No, you with me? Because the side that's this length is over there. It's not like here, yes? You guys start to see what I'm saying here. So two sides, you could even say two pairs of adjacent equal side lengths, yes? So this has got to be right next to the side that's as long as it is. This has got to be right next to the side that's as long as it is. So a trippy little shape. But can you tell me another shape we've already talked about that actually follows this definition?
A trapezoid.
What about a trapezoid? You got to be careful. Trapezoid. Would this be a trapezoid?
Oh, never mind, no.
Yeah, because what is it about trapezoid? What's the defining quality of a trapezoid?
Parallels.
It has to have one pair of parallel sides. Exactly. Exactly. Two sides are parallel. We could do this. Could everybody draw a square for me? Draw a square for me. And now rotate it. Is that a kite? Come on now. Are these two the same length? Are these two the same length? It just happens to be a kite where all four sides
Are the same.
and all four angles are the same. So is everybody kind of with me? You guys see what I'm saying? So this is the level, so this is why this level is called relationships. It goes one step beyond definitions, and you start to realize how other shapes fit other definitions. I went too far with this. Is there another shape that's not quite as perfect as a square that meets the definition of kite? Draw a rhombus for me that is not a square. Because when you draw a square, you've drawn a rhombus. But how do you draw a rhombus? Do your best to get them all the same length, yes? And if I turn it, are these two the same length? Are these two the same length? So again, kites do not give the first shit what angles are in it. They don't care about the angles. They just say these two sides have to be the same length and these two sides have to be the same length. That's all they care about. So how many things match that definition? Well, now we've got three. A general kite, a square, and a rhombus. Do you guys think there's anything else that we've already discussed that fits the definition of kite? Okay, good, because there is. So, one other little side note. Now, trapezoids are not that exotic, but there's a bit of a variant of a trapezoid that is a little more exotic. And let me see what you guys think. What about an isosceles trapezoid? What do you think is true about an isosceles trapezoid? What's true about an isosceles triangle? The base angles are same, and the sides corresponding to these angles are the same. Yes. So everybody try to draw an isosceles trapezoid. So what's funny is you can draw like an isosceles triangle and then just chop its head off, poor little guy. Pretend like I chop more cleanly. There you go. Base angles are the same measure, and the side lengths corresponding to those angles are the same length. So again, that's not a big deal. It's just a specific kind of trapezoid that's been kind of, this isn't quite, but it's kind of corrected in a way. You know what I mean? Some parts of it have been solidified a bit. So, going back to this. Oh boy, I left myself no room. Well, sort of did. Underneath trapezoid, I'm sorry, this is what I'm talking about here. Underneath trapezoid, now I got an isosceles trapezoid. Now, one's going to be a little difficult for me on this page, and probably for you too, the way you've done this. There's a kite. It's kind of like off on its own. Oh boy, the way I've done this really, let me do this. The way I've done this, let me see. It's easier if I put it in the middle. There we go. There's a kite. It's its own little thing. But then if I change the kite to have the same side lengths, it becomes a rhombus, and then it kind of goes into a square. So a square is a type of kite. A rhombus is a type of kite. Okay. All very exciting. I like it. Okay. I believe that's plenty for today, if I'm not mistaken. So, let me see. Next time we'll keep going. I didn't have any time to grade homework. I graded 3 quizzes. That pretty much dominated my weekend. So I'll try to get homework graded for you by Wednesday. Thank you for understanding.
Can I get my quiz?
Yeah, oh, if you didn't get your quiz back, I've got it here. Oh wait, where'd you go? Sign something. Where did I put it? There's Kendall.
Thank you.
Oh, I'm sorry. I put it on your desk. That's right. I totally forgot.
Do you have mine?
Oh, Kim.
Thank you.
Sure. I'm sorry I got a little scrunched up there.
Uh,
Thank you.